Hey, calculus nerds like me. So, I bet you've been asking this question. What happens if there's a hole in the object that we're rotating about an axis? Good question. So glad you asked. So, go back to your 6.2a notes and scroll down a few pages till you see these pictures, and let's get started again. So, as you can see, I've graphed, and the equation that's in black is my y equals x squared, and the equation that's in red is y equals 2x. And so I've graphed those accordingly on the axes. And of course my spin axis is the y-axis, so I've drawn my spin arrow. And then I've included in here two separate radii. If you notice, the green radii I've labeled with a capital R, and the little radii I've labeled with a pink R. And so we're going to need to use those. So if you remember from your experiences in geometry, if I wanted to find the area of this donut, just the shaded stuff, I would find the radius for the large circle and calculate the area of the large circle. And then I'd subtract the area of that middle region by finding the area of that little tiny circle and subtracting it. So that's what we're going to do in order to get rid of this hole that we're creating as we spin. So you'll notice at the top of the page I've written a formula for calculating the volume of this solid using the capital R and the lowercase r. So we're going to use the same formula that we did before when we were finding areating disks, except this time we have to subtract the volume of the inner space from the volume of the entire region. So I'm going to need both of those radii. So since my spin axis is vertical, I want to integrate with respect to y, which means I need my equations in x equals. So to find that capital R, I have to do the right function, which is the black one, which is the square root of y minus the left function, which is my y-axis, so minus 0. Of course, that simplifies. Again, notice I drew my radii perpendicular to my spin axis. And of course I solved that upper equation for x equals because I needed it in x equals. Now, the smaller radius, again, doing right minus left, well, it touches the red on the right, which again, I need to go up here and solve for x. And I get y over 2. So the right graph is y over 2 minus the left. Again, it touches the y-axis on the left, so that would be minus 0, which of course simplifies to y over 2. So now I'm ready to use my integration formula for volume, which is, if you'll notice, I pulled the pi out and just factored out the pi, and so I have capital R squared minus lowercase r squared, and again I'm integrating with respect to y. So now I'm going to substitute in both of the radii, and I'm going to go to a different page to do this. So you can see here I've substituted in both the radii, square root of y, which was capital R, and y over 2, which was lowercase r. Now, since I'm integrating with respect to y, I have to look at the y bounds. So the lowest y value, of course, is 0, and the highest y value hits up here at 4. So those are my bounds. And so now I'm going to simplify, first by squaring both parts of both radii, and integrating, I get this next equation in green, and then substituting in 4 and 0, get a final answer of 8 pi over 3. And of course, not forgetting to fill in the formulas at the bottom of our page that we just used. So there's of course how I calculate the volume, and there's the integral.